I said that in a coin flip, the probability space is head and tail. No, I should have said this, but I think in my notes, which doesn't open for some people, I got an email about that. So I'll save it as a PDF this time and send it again. Here I wrote that omega was actually the power set of omega. So it should be the power set of omega. This is omega. So sometimes we say that the power space of omega is a certain family of sets that satisfies a certain set of conditions. If you're interested, you can look it up yourself, but this is not required unless you want to study probability in a more formal way, and it's called the sigma algebra. In Google, you can type sigma algebra, and then look it up yourself if you want to. But basically, for now, just think of it as the power set of omega, but it's not always the power set of omega. It is more formally a subset of the power set of omega. In this case, it is just the equality holds. So sorry about that mistake. And I guess we can start out by reviewing. Yesterday we learned about one-to-one functions and onto functions. So question might ask, how do you know if a function, for example, this one, just a very simple function, is one-to-one or onto? And usually in math, when we talk about functions, we say that the function goes from certain space into another space. And you have to clarify where the function is going from. So instead of y, I'll just write f of x. That way we can see that the function f is going from the domain R into the codomain R. And we'll see that this is important because based on the differences in codomain and domain, the function might be onto, might be one-to-one, but it might not be. And so these are more important when we're talking about one-to-one and onto. So let's see if it's one-to-one. Remember the definition? It was that if f of x1 was equal to f of x2, then, and don't confuse this arrow, which is used in a function, with this arrow. This arrow. This arrow means implies. So don't confuse them. F of x1 equal to f of x2 will imply x1 is equal to x2. Let's think about our function and see if it implies that. So plug in f of x1 into our function, and I get 2x1 minus 3 equal to 2x2 minus 3. Well, now it's just very simple. I add 3, I divide by 2, and I get x1 equal to x2. 3's disappear, 2 disappears. Right? And it's kind of, I was confused at first when I learned this because I thought any function will be one-to-one if we apply this logic, but that isn't true. For example, if g of x is equal to x squared, then let's try doing the same thing. G of x1 equal to g of x2, then we have x1 squared equal to x2 squared. Then, can we square root both sides? And then get x1 equal to x2? Can we do this? No, we can't because, for example, negative 2 squared is equal to 2 squared, but that doesn't mean, it does not imply that negative 2 is 2. And therefore, this function is not one-to-one. On a graph, if we graph this, then we see that for this point, for any points actually, but there only needs to be at least one point where if we draw a horizontal line, then the line intersects the graph twice. So it's not one-to-one. Let's talk about onto. Is g of x, which was x squared, is this onto? What does onto mean? Say g is going from r to r. Then we know that it's onto if for any r we choose from here, we pick, I won't use this here, I'll choose r is an element of the reals, then there is some s that maps onto r. We need to find an s for each r in the codomain. That's what it needs to be onto. But obviously we can't do that for something like -1. G of x, which is x squared, is never going to be -1. And we know this because x squared is going to be at least as big as 0, but then 0 is strictly bigger than -1. And so we know that this is not onto. However, if I say that g is a function going from r to r plus, and I define r plus as the set of all reals such that r is greater than or equal to 0, then g is onto. Okay, then onto, not onto. Okay, so be wary about which codomain and which domain I'm using. So here, they're different, not the same. So this is how we prove onto and one-to-one. Okay. Let's do one more review. Let's do another example, but this time, this appears a lot of probability, and it's changing the order of our double integral. Okay, so yesterday we did a problem that was similar to this one, but today we can't really solve this. We can't solve it because I don't know how to integrate e to the y squared. I mean, maybe I do, but there's no easy way to do it. So instead, what I'm going to do is I'm going to change the order of integration. So right now it's dy dx. I'm going to switch these two, and then say it's dx dy. Note that the first d dy refers to this integral, where the boundaries are 1 and x. And the second one, the dx, refers to 0 to 1. And so when we change the integral order, here's the wrong way to do it. Here's the wrong way. The wrong way to do it is to just switch the integrals like that. And this is wrong because you don't know how the bounds, you didn't take into account how the boundaries changed, how these numbers right here, how they changed. So we'll think about these. So right now, remember that when we're integrating, when we're doing a double integral over a surface, then we are actually having an area, right? Yesterday I gave the example of A, B, C, and D, and how when we integrate over this, then we get the volume that looks like that. And so we need to think in this way. For example, in this example, we had x going from A to B, y going from c to d. If it was like this, then we can change the integrals without worrying about anything. But because we have an x in our boundary, we have to be wary of this. So let's keep this in mind then. Think about the bounds. First of all, the y goes from x to 1, right? The dy. And therefore, y is going from x to 1. Okay, so we can write down this inequality. Similarly, we can write down the inequality for x. X is going from 1 to 0. But then we're changing the order of integration, and so we're going to combine these two inequalities and say that 0 is less than or equal to x is less than or equal to y, 1. Okay, did everyone follow so far? Yeah. Okay. So now we want to change the order of integration. First we want to go for x and then go for y. And so now our new bound is from 0 to y. Okay, and so we leave the function inside, and then for the boundaries we'll have 0 to y. And then for dy, we'll have, notice this part, y is going from 0 to 1. And then inside I'll have my function, e to the y squared. And notice that if I just switch the order of integration without caring about the boundaries, then my answer here would have been wrong because the boundaries are wrong. Here it goes from x to 1, 0 to 1, but actually the correct answer is 0 to 1, 0 to y. And so you need to keep this in mind and then think about where the boundaries are going. And now we can compute this integral easily, because if we integrate the inside, then I have no x here, and so this e to the y squared is treated as a constant, and therefore the middle step is e to the y squared from x e to the y squared, and x goes from 0 to y, and therefore if I plug in 0 into x, then I'll just get 0, and so this just becomes 0 to 1 y e to the y squared dy. And now I know how to integrate this, because I can use the chain rule backwards. I can say, if I derive e to the y squared, if I derive it with respect to y, I'll get 2y e to the y squared. And therefore, if I integrate both sides, I'll get e to the y squared is equal to integral twice the integral of y e to the y squared. And so if I just multiply 1/2 to each side, then I'll get my answer. And therefore, the answer is 1/2 e to the y squared. Y goes from 0 to 1. And if I plug this in, then I'll get 1/2 times e to the 1 minus e to the 0, which is just 1. And this is my answer. Did everyone follow? Any questions? Okay. Hopefully this is review. You may have learned this many years ago, but I'm pretty sure you learned it. Do you need more time to write it down? If you do, then just okay. So today we're going to start learning about counting. We're going to do this because then we get an easy way to learn about, to calculate the probabilities. So let's start with the basics. Let's talk about letter rearrangements. Rearrangements. For example, if I have A, B, C, and I rewrite this, and I reorder it, A, C, B, and then I'm going to count all the ways I can uniquely reorder them. But a quick way to do this is to note that there are 3 letters. For the first choice, there are 3 letters, and so there are 3 choices. For the second choice, one of the letters got used, and there are only 2 choices. And for the remaining one, it's just 1. And so there are 6 ways to choose, 6 ways to reorder A, B, C. I'm not going to write all of them, but you can check that it's going to be 6. It's a little bit more complicated if I write a 3-letter word that is repeated. In this case, we have to think about what we divide out by. First of all, again, it's going to be 3 times 2 times 1 for the same logic that we used above. But then we have to divide out by, for example, if I label the first C as C1 and the second C as C2, then I can reorder the C1 and C2. And how many ways are there for me to do this? There are 2 times 1 ways to do this. A classic example would be how many ways are there to reorder. So for completeness, I'll just say that there are 3 ways to reorder it. It's clear because the 3 ways are the 3 places that L can be. As soon as L is decided, then the 2 C's are decided. A classic example is Mississippi. Here there are 4, 5, 6, 7, 8, 9, 10, 11 ways to reorder the letters. And so on top I'll have 11 factorial. But then I divide out by the number of ways that I can be reordered. There are 4 I's. And then there are 4 S's. And there are 2 P's. There's 1 M, so I can divide by 1 factorial, but then I don't need to. So hopefully this is simple enough. And next, I'll talk about permutations. So let's say that we have 8 runners in a race, and then only 3 of them win. But then the winners are counted differently. There's going to be gold, silver, bronze. There are no ties. No ties in the race. And how many ways are there to, if the runners are all different, how many ways are there for the ceremony to take place? In how many different ways can they win? Well, this is easy if you think about it. There are 3 places, and there are 8 choices for the gold medalist. And then there are, because one person is fixed, this is fixed now, there are 7 remaining runners who can become second place, right? So that would be 7. And similarly, there are 6 runners left to take bronze. So it will be 8 times 7 times 6. Another way to write this is to note that these are decreasing in order, and therefore we could have said 8 factorial divided by 5 factorial. Right? But then you can note that how did I get the 5 factorial? Well, I got it using the 8 and 3, and therefore I can rewrite this even more cleanly into 8 factorial divided by 8 minus 3 factorial. Okay? This is NPK. Permutation, where we're choosing, out of the n people, we are choosing 3, and the 3 are treated differently. Okay, now we'll talk about NCK. I'm sure you all learned this in middle school, but And CK is if we have 8 runners and then 3 gold medalists, just 3 winners. We don't give them gold, silver, bronze, we just give them 3 gold, the first 3. So how many ways are there to choose that? Well, for that, that's just, there are NPK ways to choose them differently, but now the gold, silver, bronze are going to be weighed in the same amount. And therefore, the gold, silver, bronze, gold, bronze, silver, and then I reorder them. How many ways I can reorder them? I can reorder them in 3 factorial number of ways, right? Because gold, silver, bronze can be reordered in 3 factorial ways. And so I divide it out. I divide it out because I shouldn't have reordered them. So maybe there was an easier way to find out the combination formula, but this is the way that I remember it. And so the permutation formula is n factorial divided by n minus k factorial. Here, notice that 3 is the k factorial, and so it'll be n factorial divided by n minus k factorial. This is the npk part, divided by another k factorial. Okay, so in mathematics, combination, nck, is used a lot more than npk, and so we even give a special notation for this. You may or may not have seen it. And it looks like a fraction, but it's not. It's just parentheses with 2 numbers, 1 on top, 1 on bottom. Usually the top one being bigger. So that's n choose k. And now let's think about this equation right here. N choose k is equal to n choose n minus k. Okay, we can plug this into the formula and then check that this is true. So proof. There are 2 ways to prove it. I'll use the brute force way, but I'll also use the combinatorial way. And I'll show you both. N choose k is equal to, I plug it into the formula, and I'll get this one, right? And then, so this is the left-hand side. On the right-hand side, I'll have n choose n minus k. I plug it into the formula. I have top divided by bottom. And then I'll have n minus k factorial. But note that n minus k is just k, right? So this part is just k. And note that these 2 are the same. And therefore, they're the same. You can plug in numbers like 8 choose 3. Check that it's the same as 8 choose 5. But there's a better way to prove this than just using arithmetic. Another proof is a combinatorial proof. And this is the only type of proof in mathematics that doesn't use that many equations, that just talks. So a combinatorial proof will go like this. Choosing k out of the n. So for example, let me use the example 8 choose 3. Choosing 3 winners out of the 8 runners is the same as choosing the 5 losers out of the 8 runners, right? As soon as I choose out of the 8 people, if I choose which 3 runners are going to win, that's like choosing which 5 runners are going to lose. And if I count the winners, it's the same as counting the losers, and therefore there is a bijection. Remember bijection? We talked about this yesterday. 1-to-1 onto. There's a bijection between the winners and the losers. And between the way we choose the winners and the way we choose the losers. And therefore, we know that n choose k is the same as n choose n minus k. Okay, did everyone follow? Next, let's look at some more examples of a combinatorial group. For example, this looks a little bit more complicated than what we did before, but if we really think about it, then we will get the answer. First of all, if we don't use a combinatorial group, then imagine how much effort this is going to take. We can either use brute force, but then we'll have to do it for every k, and then we have to add them. We also have to square it, and so it's going to be a monster term on the right side, which turns out to be very clean on the left side. But there must be an easier way to do it. Another way to prove these kinds of statements are to use mathematical induction. Mathematical induction. Note that this word, induction, in English, is used, there are many definitions of induction, but the one that we're referring to is kind of a misnomer because actually all of mathematical reasoning is deductive reasoning. It means you start from axioms and you work your way through. And there is no way that if your axioms are true, then the theorems must be true. There's no way for the theorems to be false. So we are absolutely certain when we use deduction or deductive reasoning. But inductive reasoning, on the other hand, is used by statisticians and other sciences. Inductive reasoning, we try to look for a cause. For example, I ate medicine and then I got healed. And if I see this happening a lot, then maybe I can infer that this medicine heals me. But note that you can't ever be sure about what's actually healing you. It might not be the medicine. Maybe the medicine helps in some way. And in economics, we can use quantitative reasoning to, maybe in econometrics, we can kind of try and see about how much is medicine helping us. But anyway, we can't ever be sure that it actually is helping us. On the other hand, in deductive reasoning, we are absolutely sure, 100% sure. Anyway, induction is a form of deductive reasoning, not inductive reasoning. So don't get confused about these two English words. Anyway, mathematical induction goes like this. Imagine dominoes. And let's say that the first one gets knocked down. And I know that if the kth one gets knocked down, then I know that the k plus 1 also gets knocked down. Then I can be sure that because the first one knocked down, then I can use this part reasoning and say that because the first one got knocked down, the second one got knocked down. Because the second one got knocked down, the third one got knocked down, and so on and so forth, and therefore this is true. Every single one got knocked down. I can say that. And this is true for counting numbers, right? Because mathematical induction actually comes from, it can be derived from the well-ordering principle talked about in set theory, but we won't get into that. Instead, maybe we can look at an example of mathematical induction. Maybe we can prove that if I add every number from 1 to n, that the sum is going to be n times n plus 1 divided by 2. Right? I can use mathematical induction on n. So step 1. I need to make sure that the formula works for n equals 1. Then on the left-hand side, I'll have the sum from 1 to 1 of k, which is just 1. On the right-hand side, I'll have 1 times 1 plus 1 divided by 2, which is just 1. And so the formula works for the first one. Second step, if I know that the formula works for the kth step, then I want to prove that it works for the k plus 1 step. And maybe I should not use the word k. Maybe I should use the word n because k is already being used in the formula. So that we don't get confused. So suppose that the formula works for the nth one. Then for the n plus first one, this is equal to, I can decompose this into the first n being added together, and then the last one will be n plus 1, right? I decompose the summation. So first, I'm adding the first n, and then I'm adding the last one. Okay? And then I'm going to use the formula because I know that, I suppose that for the nth one, the formula works. And so I'm going to use the formula here and say that this is equal to m times n plus 1 divided by 2 plus n plus 1. Right? This is the most important step, and so there's a special name for it. This is called the step by inductive hypothesis. You might come across this in mathematical literature. This is what it means. We are using the fact that the formula works for the nth one, and therefore we are substituting the formula. And notice that for the next equation, we have an n plus 1 both here and here, so I can factor it out. And I'll get m over 2 plus 1, right? If I multiply this out, I'll get here, I'll get this one. Hopefully you see it. And then what I'm going to do is I'm going to combine what's inside. So that'll be n plus 2, right? Because 1 is equal to 2 over 2. And so I can add the fractions. And then I can say that we're done because this is equal to n plus 1 times n plus 2 divided by 2. And therefore, our formula works for n plus 1. If I want to be really clear, then I can even say this is equal to n plus 1 times n plus 1 plus 1 divided by 2. So I proved that if our formula works for the n terms, then it also works for n plus 1. And in mathematical literature, you might see a proof that looks like this, and the induction will be on n. That's what they will say. Using induction on n. Notice we're not using it on k because k is just a dummy variable. Okay, so we can use something like this, but notice that there are pros and cons for mathematical induction. Pro. It's very easy. If you are seeing this for the first time, then it might be hard, but then if you just practice this for about a day, then you can get the hang of it. And you can prove things that you don't understand using mathematical induction. And that's why there's a con. The con is you might not understand. You might not understand why the formula k is 1 to m of k is equal to n times m plus 1 divided by 2 works. Instead, a better proof for this might be you add all the terms all the way to n. And I want to find this out, right? So I'm going to say that this is my sum s. And then I add it in the other way, 1 plus 2, all the way till n minus 1 plus n. And then I add the 2 equations, and I'll get 2s is equal to n plus 1 plus, I add n minus 1 and 2, and I'll get n plus 1. Notice I get n plus 1 for all of these. How many n plus 1s do I have? I have n plus 1s. And therefore 2s is equal to n times n plus 1. And therefore s is equal to n times n plus 1 divided by 2. This is the way Gauss proved it. And this is a much better proof than induction because now we know why the formula works. But induction is still a valid proof. What matters is, did you understand? And so instead of proving this one, let me write it again down there. Instead of proving 2n choose n is equal to k from 0 to n of n choose k squared, instead of using mathematical induction on n, maybe there's another way to do it. So let's think about combinatorial proof. Okay, so I'm going to draw a picture. And there are n people here and n people here. So I have 2n in total. And out of the 2n, I am going to choose n. So maybe for n, I can say that n is 5. And out of the 5 n's, I'm going to choose, the 10 n's, I'm going to choose 5. Maybe like that. And I'm going to think about how many ways there are to choose this. But notice that as soon as I choose 2 from this half, imagine that I can't look at this side. I'm not allowed to look here. Okay? But I will still know that 3 are getting chosen from the right side, which has a curtain, right? I'm not allowed to see it, but I'm only allowed to see my half. But I see that only 2 people got chosen from this half, and so obviously 3 people got chosen from the other half, right? And therefore, every time that I have n choose k from my half, I will know that n minus k got chosen from the other half. And therefore, if I multiply the 2 together, then I will have the number of ways that I am choosing k people in total. Right? But how many people got chosen from my side? Well, that could be anything from, if no one got chosen from my side, okay, there are 2n people, n are being chosen in total, right? I have n people on my side. I can have nobody get chosen from my side, right? So that would be n choose 0 from my side, and that would be n choose n from the other side. And that's why, and note that, okay, and that's why we start at 0. And we go all the way up till n because all n people can be chosen from my side, right? And all the k's in between are also possible. 1 person could get chosen, 2 people get chosen, and so on and so forth. That's why we add all of them. So why is it being squared? Why is it being squared? Well, note that, remember, we proved before that n choose n minus k is equal to n choose k, right? Because choosing the winners is the same as choosing the losers. And therefore, When I multiply n choose k by n choose n minus k, I can rewrite this as n choose k times n choose k. And that's why it's n choose k squared. And the k can be viewed as the people that are being chosen from my side of the curtain, but then that k can go anywhere from 0 to n, and that's why there is a summation from 0 to n, and we multiply them, and we multiply n choose k by itself, and we add all of it, and then we'll get the total number of ways we can choose n people out of 2n. We'll take a short break and resume at a little bit after 11.